Have you ever seen a headline about a scientific study and thought, wait a minute, that doesn't quite add up? Well, today, we're diving into a story where the math literally doesn't add up. It's a kind of detective story hiding in the pages of top scientific journals, a case of mistaken identity, inflated numbers, and what it all means for how we understand science.
All right, let's start with a really simple, fundamental rule of, well, reality. You can't have more than 100% of something, right? 100% is everything. It's the whole pie. So what on earth does it mean when a scientific study claims it can explain more than the whole pie?
It sounds like a trick question, doesn't it? Because it's logically impossible. You can't account for 110% of why a plant grows, or 120% of the reasons people choose coffee over tea. The math just completely falls apart. And yet, when researchers took a really close look at studies in some of psychology's most prestigious journals, they found exactly that.
153%. That is a real number. A 2004 paper found that when they added up the effects from a sample of studies, researchers were, on average, claiming to explain over 1.5 times the thing they were studying. It was so absurd, so obviously impossible, that it demanded an explanation.
So what's happening here? Is this just bad science? Well, not exactly. It's way more subtle than that. This is a detective story where the culprit is a really common and very misunderstood statistical metric. This isn't about fraud. It's about a widespread reporting error that pumps up the results, a lot of the time without the researchers even realizing it. And to solve this, we need to meet our too many suspects.
The whole mystery boils down to a statistical measure called Eta-Squared. You know, the Greek letter eta squared. It's just supposed to tell us how much of an outcome is explained by a certain factor. But here's the twist. There isn't just one Eta-Squared. There are two, and believe me, they tell very, very different stories.
On one side, you have classical Eta-Squared. Think of this as the whole pie view. It's simple, it's honest. On the other side, you have partial Eta-Squared, the zoomed-in view. Now, this one is a useful tool for sure, but it's also the source of our entire problem, because it can make effects look way bigger than they actually are. Let's see how that works.
So let's start with the straightforward one, classical Eta-Squared. Imagine you're trying to figure out what causes student test scores. Maybe 10% is explained by how much they studied, 20% by how well they slept, and 15% by their diet. Classical Eta-Squared measures each of those as a slice of the entire pie. And because all the slices have to come from the same pie, if you add them up, they can never, ever be more than 100%. Makes sense, right?
So when you look at it this way, effect A is a modest 10% of the total picture. You add in effects B and C, and that big chunk that's still unexplained, and everything is in its proper place. It all adds up to one whole pie. This is pretty much how we all intuitively think statistics should work.
Okay, now for our other suspect, partial Eta-Squared. This one is, well, it's a bit slippery. To calculate the size of effect A, it first removes the influence of all the other known factors, like B and C, from the equation. So it's not measuring effect A against the whole pie anymore, it's measuring effect A against a much smaller pie, just the slice for effect A plus whatever is left unexplained.
And look what happens here. This is the exact same effect A from before, but by using partial Eta-Squared, by ignoring B and C, it suddenly jumps from 10% to 19%. The effect itself isn't any stronger. The metric just zooms in to make it look bigger. Now, imagine you do this for every effect in a study. You can see how the total just blows past 100%. And just like that, our mystery is solved.
So there it is. That's the smoking gun. The problem isn't that partial Eta-Squared exists. It actually has some legitimate uses for isolating variables. The problem is when researchers report this inflated zoomed-in number, but they label it as if it's the simple whole pie number. And for years, major statistical software packages actually mislabeled the output by default, which helped this become a really widespread and often totally unintentional error.
So how does this actually play out in the real world? Let's look at a specific case from a published paper where, well, the math was just obviously wrong. Back in 2002, a study was published in Psychological Science, which is a top journal. The researchers were testing something called decision affect theory, which is basically just a fancy way of looking at how our expectations influence our feelings about an outcome. And based on their results, they concluded the theory had strong support. The study looked at two main things: what grade a student expected to get and the grade they actually received. The paper reported that the expected grade accounted for 46% of their emotional response. Okay, and the grade they actually got? That supposedly accounted for a massive 85%.
Now, you definitely don't need to be a statistician to see the problem here. 46% plus 85% equals 131%. These two factors alone claim to explain 31% more than the entire phenomenon they were studying. This is a giant red flag that the numbers being reported were those inflated partial Eta-Squared values, not the real ones.
So, just how big was the inflation? Well, researchers went back and recalculated the correct whole pie number. For that first effect, the reported value was 46%, but the actual value? It was just 11%. The finding was inflated by more than 4 times, and that's the difference between something being a major driving factor versus just a minor contributor. Suddenly, that strong support for the theory looks a whole lot weaker.
And look, this isn't just about one study getting the math wrong. This quiet, often totally invisible error has a massive ripple effect that distorts our scientific understanding in some pretty important ways. This error creates 3 huge problems. First, you get flawed theories built on shaky foundations. Scientists might chase ideas or build entire research programs on an effect they think is powerful when really it's pretty minor. Second, it corrupts meta-analyses. You know, those studies of studies that combine data from tons of papers to get a final answer. But if the studies they're using have these inflated numbers, then the conclusion of the big review will be inflated too. Garbage in, garbage out. And finally, it can lead to misguided interventions, promoting expensive educational programs or health policies based on exaggerated evidence. But maybe the most concerning part of all this is that the error is usually invisible. In that 131% case, we only caught it because the sum was so obviously impossible. But what if an effect is inflated from, say, 2% to 6%? That's a 300% increase, but it's not going to raise any red flags. And because researchers often don't publish the raw data you need to check the math, we honestly just don't know how common this is. It's a really powerful argument for open science, where data is shared so anyone can verify the results.
So what's the final verdict in our little statistical detective story? Well, the answer isn't to stop trusting science. Not at all. It's to remember that science is a complex human process, and it's full of potential pitfalls, just like this one.
The goal here isn't to be cynical. It's to be sophisticated. This whole story teaches us that the details of how science is reported matter a lot. Knowing the difference between a whole pie and a zoomed-in number makes you a sharper, more critical reader of scientific news. And it's a huge call for more transparency, not just in the data, but in how scientists explain their findings to the rest of us.
So I'll leave you with this. The next time you see a headline about a major breakthrough or a large effect, just ask yourself, are they showing me the whole pie, or are they just showing me one zoomed-in slice?